guys, this is our final makeup lecture for the semester on section 4.6, Fundamental Theorem of Calculus, part 2. Again, just as a reminder, I will be abbreviating this guy as Ftc Ii through most of the lecture, so just be aware of that. What I want to do before we jump into figuring out what Ftc Ii is just recapping really quickly a couple of things that we'll need to be able to derive and apply this. First off, we mentioned last class Ftc Ii was a link between the definite integral and antiderivatives. So just a refresher, what are antiderivatives? Antiderivatives are these things that undo the process of differentiation. As a comment, the most general antiderivative of a function, whenever you antiderive something, find the function that you derived to get there, you need to throw a plus c on the end of that. Reason being, if you derive the plus c, it goes away, right? So you don't know what constant was on the end of your function to begin with. Here, if I wanted to try this particular example that I have worked out, have this long string of functions that I'm looking to antiderive. Most of your antiderivative rules were just the derivative rule backwards, but there were a couple special cases, things like power rule here. If I work on this term by term by term, what I get back for this particular example, if I can get my pen to cooperate, first piece, we hang on to our coefficient for constant multiple rule. I antiderive using power rule. What you do for power rule is add 1 to the exponent up top and divide by the same number. I'll move on to my next term. I'm looking for the antiderivative of secant squared. This is a case where the antiderivative is just the reverse of the derivative rule. The thing you derive to get secant squared is the tangent function. Okay, for the next guy, the next couple of these actually, these are mostly functions that are the reverse of the derivative rule. The thing that you derive to get 1 over root 1 minus x squared is the sine inverse function. The thing that you derive to get e to the x is the exponential function itself. And the thing that you derive to get 1 over x is the natural log function. And again, since we took an antiderivative, if I want the most general case, I need to throw a plus c on the end. Okay? At this point, there's probably not too much simplification we could do unless perhaps we wanted to rewrite the beginning piece here. You can simplify that. It's 2. But at any rate, this is our antiderivative for this particular function. I'll give you guys another example. Here we're going to go in a slightly different direction. I'll go ahead and ask, what's the derivative of this function? Well, okay. If we take the derivative of this, you have to hang on to the constant coefficient out front. You'll notice we have a composition of functions here, which requires chain rule. My derivative of sine is the cosine function, and the derivative of my inside, 6x, my derivative of that is just 6. Now notice, I get a cancellation, so I've got that the derivative of that above function is just cosine of 6x. Now here's the reason that I bring this up. What this is going to suggest is the following. If I gave you guys an antiderivative to evaluate of cosine of 6x, now this isn't a basic rule kind of like the ones that we've seen before, it's just slightly different because we've got a constant out front. Having seen the above example, I can tell you what the antiderivative is because we know the thing that we derived to get there. This tells me that I'm expecting 1 over 6 times sine of 6x, but again, even though there wasn't a plus c there up top originally, for our most general case, we have to add a plus c on the end. Now some comments on what's going on and why I wanted to point this out. We aren't used to seeing these expressions in antiderivatives that have, a kx on the inside. But these are pretty straightforward antiderivatives to take care of if you know the original rules, because the only thing that's going on is this. If you have a kx on the inside, what that means is you probably took a derivative of a function that had a kx on the inside to begin with. Now when you derived that, we had to do chain rule on this. right? So we ended up having to multiply by the derivative of the inside. And the reason that we got down here to having no coefficients on the function that I was looking to anti-derive, okay, this cosine of 6x term, the reason that I got there is because when I did chain rule, the constants canceled. Okay, the 6 and the 1 over 6, they went away. So here's how I undo my kx functions, or here's how I anti-derive my kx functions. You'll notice that the basic rule that I was using, cosine turns into sine, that worked totally normally. The only thing that we really have to do that's special is, one, make sure that we copy over the inside function just like it was originally. That didn't change. And then two, make sure that you're dividing by whatever your kx is out front, right? If I wanted to check my work, I would have to derive 1 over 6 times sine of 6x plus c. If I go to derive that, chain rule is going to have me multiplying by a 6, okay, because of the inside function 6x. So if you see a kx function, you're going to have to divide by that k when you take the antiderivative. If that explanation is a little bit fuzzy to you, I actually have a whole chart of the kinds of functions that you guys would run into that look like these kx antiderivatives. These hopefully kind of spell it out, right? Like here up top, if I have e to the kx, we're going to apply our exponential rule. Just normally, antiderivative of e to the something is e to the something. But since there is a kx, and I'm trying to undo chain rule, I have to divide by k. Right? If chain rule has us multiplying by k and we're trying to undo chain rule, we want to do the opposite of multiplying by k. We want to divide by k. Okay, and the same thing holds for pretty much all these trig functions as well, right? We just saw one of the cosine ones. It works for all of these other rules as well. Now, other things that I wanted to work on before we jumped over to Ftc Ii. Let's do a brief recap of what we talked about last class. This is a fundamental theorem of Calculus 1. It gave us instructions on how we could derive a particular setup of the definite integral. Now, this is specifically the case where your upper bound is the same variable as you were deriving with respect to. So if you got a definite integral that had numbers in both of these slots, remember that's giving you a explicitly defined area of a particular region. That would come out to a constant, and derivatives of constants are 0. So I'm not talking the general derivative of a definite integral, but this special case where we've got an x up top in my bounds. If I go to do that, take that derivative of that definite integral, we basically get back the original function, but in the variable x. So the trick that I'm making note of here is these guys match, so I just get to plug my variable x into my function. I don't have to do the work of computing what that area is. I don't have to actually take a derivative. I can just direct substitute the x in and then call it good. Okay. Similar deal down here, but you'll notice that we've got the wrong quantity up top. Right? We needed the x up top to get my order straight. The way that we fix this is make sure that you put your x in the right spot. This is going to involve flipping your bounds, but as we mentioned before, anytime you flip your bounds, you introduce a sign error, or perhaps you correct a sign error that was already there. At any rate, if you flip your a and b on your bounds for your definite integral, you introduce a negative sign. So I've now got a negative secant function instead of a positive secant function. I can make this observation that now my variables match as desired for Ftc 1, and I can just take that variable and substitute it into my function. Okay, I'll get negative secant of x. Now, question, can I find a direct way to evaluate my definite integral? We don't have a way to do that yet. We just have a way to derive this special case of the definite integral. So can I find a way to maybe apply this in a more useful setting, right? We've mentioned that it might be pretty useful to be able to find areas, there are direct applications, like, trying to figure out how much paint you need or how much material you need to build something. But there's also the question of if your function represents some measurable quantity. If you do the dimensional analysis on the units, the area might represent some other measurable quantity that you're interested in. How do I evaluate that thing, right? I'm not immediately concerned with, directly having an application for needing that derivative. How do I just find the area in the first place? Well, we'll build towards that, and thankfully the proof of it goes a little bit faster than what we did for Ftc Ii yesterday. I'll start out with a couple observations. Here's the first one. This is that area so far function that I introduced last class. G of x is my definite integral from a to x of f of t dt. If g is my area so far function, then when I'm looking for a definite integral of f, I can turn to that area so far function. I can just evaluate what's going on in the endpoints. Now, if you're looking for a reason for why this works, well, let's look at what g of b minus g of a actually is. It's just what happens when I take b and I plug it into this function x, and same deal over here, plug a into x. Now, where do you plug stuff into the function g? Well, you'll notice that the only place where my x pops up in my function is that upper bound. So this is going to be my integral from a to b f of t dt for g of b. And then g of a is going to be what happens when I plug a into that upper bound. Now, we've gone over a couple algebraic properties of definite integrals. You notice that any time that both of these numbers on my bound are the same exact thing, this is just me integrating over a single point, right? My interval of integration has no width. Now, if your interval of integration has no width, your region that the signed area from that definite integral represents has no area. So, we've discussed this thing just goes to 0, right? If that guy equals 0, this means that your overall expression, well, let me go ahead and just throw the equal sign on here. That should be an A. This expression, just drops off. So, I'm left with just my definite integral from a to b of f of t dt, okay, which is what the initial claim made in the first place. So, we'll keep that information in mind. If I want to evaluate the definite integral, think about plugging the endpoints into my area so far function. Now, great. I get to evaluate this using my area so far function, but that sort of presupposes that I know how to find area in the first place, right? Because that function is defined in terms of a definite integral. This is where we introduce note 2. Now, since g is this area so far function, and we have the fundamental theorem of calculus 1, we can note that a way that we could think about getting to g is that it is some sort of antiderivative of f. Now, why? Again, I want to think about Ftc Ii. If I take a derivative of g, this is the same as me taking a derivative of this definite integral. And this is that case that we mentioned before, that you just get to plug x into your function. Okay, you get f back. So in other words, I'm saying g prime of x is equal to f of x. Or if to go from g to f you derive, this means that to go from f to g you get to anti-derive, right? So g very definitely is an antiderivative of f. Now, great. We pair notes 1 and 2. We know that we should be able to take a difference of g of b and g of a to get my definite integral back, but which antiderivative of f is this, right? How do I know which one to use? Well, observation number 3 it doesn't matter actually which antiderivative we use. You could use a general antiderivative to compute this and not necessarily just, the area so far function g. Now, if I'm looking for a reason for this guy, antiderivatives only vary by constants, right? So antiderivatives may differ by, at most, a constant plus c on the end. We said for your most general antiderivative, you throw that plus c on because you don't know what plus c you started with. So, a way to interpret this here is maybe if my general f versus my g area so far function, if these are both antiderivatives, I could go ahead and think about my f of x as being, I don't know, just g of x plus some constant on the end. Maybe I got the constant wrong and I needed to offset it a little bit, right? So if I know that these guys are offset by a constant at most, well, f of x, or let me look a little bit more specifically here, f of b minus f of a, this is just going to be the same exact thing as if I substitute in this top line, right? So instead of using f, I can use g plus c. That means that for this first piece, I've got g of b plus c. That's really the same as f of b. And then for the second piece, I've really got g of a plus c. That's really f of a. Now, if I'm performing this, my c's are going to cancel. I just get g of b minus g of a. So honestly, regardless of whatever the constant was, if we got one antiderivative versus another, it doesn't matter. You can use any antiderivative to pull this trick. Now, if I throw all that together, what I'm getting is the fundamental theorem of calculus part 2. The conclusion of those last 3 observations, that if we have a continuous function, that was an initial assumption for Ftc Ii. If I have a continuous function, then I can evaluate my definite integral from a to b of f of x dx by taking an antiderivative and then substituting in my bounds, right? So this is my antiderivative with my top bound substituted in minus my antiderivative with my bottom bound substituted in. And again, by that last note, we didn't need specifically the area so far function. We could just take any old antiderivative of f, including the ones that we get by using our antiderivative rules. So, comment on notation here, because I'm assuming this middle bit is probably a little bit mystifying. We haven't used that notation so far. I'll go ahead and note that middle step. This guy is just to keep track of my antiderivative, okay, and my bounds. The way that I want to read that, okay, this middle step, I'll go ahead and underline this guy in red here. What this basically says is evaluate f between my interval a and b, my endpoints a and b, okay? So it's really just kind of a placeholder step. We hit this point where we've taken an antiderivative, but we haven't plugged the bounds in yet. We can remind ourselves, what antiderivative did I just get? And we can also remind ourselves, okay, well, what bounds do I need to plug in later? So that's all this middle bit here is about, okay? Now, comment number 1, before we get to, explicit examples with cranking this out, I will make a note that this does give us an alternate view of the fundamental theorem of calculus part 1. I mentioned last time that there's a, not a consensus on which one's Ftc Ii, Ftc II. You can use one to prove the others. So different people will bring these up in different orders. I did Ftc Ii first because it gives us a nice recap of some of the lessons that we've seen before in class. But I will admit, the proof in the other direction, the proof of Ftc Ii given Ftc II, it simplifies a lot. Reason being, if I go to evaluate this derivative of this definite integral, I can work from the inside out. First thing I can do is try to figure out that definite integral, and the above theorem said that you can antiderive, and then just remind yourself what you need to plug in. At this point, I can go ahead and plug stuff in. We always substitute in the top bound first, and then you subtract off what happens when you substitute in the bottom bound. And at this point, we can go ahead and take a derivative. Now, your derivative of capital F, I'll just go ahead and write as capital F prime. This guy over here, if you think about what we just did, we're making this assumption that A is some sort of number, okay, that bottom bound, A is some sort of numerical quantity. That means you plugged a number into a function. This guy is going to be some sort of number. So when you go to derive it, it falls off. We're stuck here with this derivative of capital F, but if capital F is an antiderivative, it just derives to F. Okay, so this is a little bit faster to view this. If you ever find yourself needing to use Ftc Ii for something, but you don't quite remember what gets plugged in where or what your result is, you know, it's not too hard to derive just using Ftc Ii. Now, at any rate, where we are probably more concerned, actually doing examples involving Ftc Ii, right? How do I evaluate definite integrals? Well, here's an example of one that we actually already know how to do, right? There was an old method for this. It was that your definite integral from a to b of c dx, this is the same thing as c times b minus a. So here, if I fill that in, this is c times b minus a. 6 minus negative 3 on the end. If I clean this up, this is minus 8 times 9, or minus 72. Let's see if we can try this with my new method. Okay, so if I can try this with Ftc Ii. What Ftc Ii said to do is you want to, take this function. I'll just copy it down here for reference sake. You want to antiderive this. If you antiderive the function negative 8, you antiderive a constant, you just tack on a variable. You'll get minus 8x. This has to be evaluated between minus 3 and 6. Okay, that's what that notation was there for, is just as a shorthand to remind us, hey, I've antiderived, but I haven't plugged stuff in yet. Now I can go ahead and plug stuff in. You always want to substitute in the top bound first, and when I say top, I mean physical location, looking at the numbers on the page. I don't necessarily directly mean the larger number, just whichever function actually appears on the upper part of that notation. Plug that guy in first. We've got minus 8 times 6 minus 8 times negative 3. If I clean this up, this is minus 48. There's a lot of signs here, but at least two of them cancel. Minus 48 minus 24, and if I clean that up, we get the same exact result of minus 72. So this does match up with our old methods, and it gives us reasonable answers here. Now comment, and I will spell this out. The theorem states that my f, my capital F that I use here, is going to be any antiderivative, right? Any antiderivative. We didn't have to use specifically the area so far function. We could use capital F. Since I can use any antiderivative, that means I don't necessarily need the plus c on the end, because if I wanted to, I could choose the option that I didn't have a plus c on the end. Okay, choose the case that c is 0. Now, a reason for this, remember back in that step where we were showing that the difference between f of b minus f of a, and g of b minus g of a didn't matter because those plus c's canceled. If you do the plus c on your work, it's going to cancel the exact same way. So if you really, really wanted to, you can throw that plus c on the end when you're performing this, but do note that at some point you're going to get a plus c minus c when you're in your work, so you don't really need it in the first place. This is why, my steps to evaluate my definite integral, we antiderive. Okay, we got this capital F of x evaluated between my endpoints. I don't need the plus c here, because if I put a plus c here, I will get a plus c here, and I will get a plus c here that I am subtracting off. So eventually those will cancel. Okay, the only things I need to worry about are antiderive to get capital F, and then plug in my bounds. Okay, and you're always subtracting top bound minus bottom bound. Okay, let's try this on a couple more examples. If I want to evaluate, we just said antiderive first, and then substitute in bounds. Here, if I want to try that, my antiderivative of 2x is I hang on to my constant coefficient 2, and then I apply power rule on x, because x is really x to the 1. Anything to the 1 is itself. If I antiderive x, I get x squared over 2. If I antiderive 4, I get 4x. This has to be evaluated between 0 and 3. If I want to make my life a little bit easier, I can go ahead and take care of these cancellations on the end. I don't need those 2's. I really can just think about what happens when I'm taking x squared plus 4x and evaluating at these bounds. Now, as a comment, when I go to plug stuff in, this will give me basically 9 plus 12 here, and then, minus 0 plus 0. We can go ahead and simplify this. We're going to get back a definite integral of 21. If I wanted to do something similar for this case, first step that I need to do is take an antiderivative. Now, maybe this is not a familiar form to recognize what antiderivative I need to take. To really emphasize, I'm going to rewrite this a little bit. This is the same exact thing as 10 times 1 over x, right? If you multiply fractions, you just go across the top like this. So constant multiple rule says I can hang on to my 10, and I derive 1 over x. This is my rule for natural log. And this needs to be evaluated between 1 and e. We always plug in the top value first, and then you subtract off what happens when you plug in the bottom value. Now, if you remember how our natural log rules worked and what the natural log function looked like, the natural log and the exponential function are inverses, so they cancel each other out. What am I left with here if I cancel out? Well, anything is really itself to the 1. So when my log and e cancel, this is really going to be 10 times 1, that leftover exponent. Over here I'm subtracting off 10 times natural log of 1. Well, your natural log function looks basically like this. If you plug in 1 to natural log, you just get 0 back. So that'll drop off, and this guy will simplify to 10. I'll try and do a couple more here, like perhaps this guy. And as a reminder, antiderivative rules are a little bit like derivative rules in that, there were a couple special cases. If I wanted to derive a function that looked like this, I either would have to do product rule or simplify to multiply this out. So what that's going to suggest about going backwards, if you're trying to undo a process that requires special rules for products, quotients, and compositions, undoing that process is probably going to require special rules too. So I will go ahead and note, if I wanted to try something like, like t squared over 2 times t squared over 2 plus 3t, please, 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 please don't do that. That's definitely not going to help you out here. If I was deriving, I would need product rule. If I'm anti-deriving, I need an analog to product rule. We don't have that yet. So keep in mind, these cases with products, you can't directly work with them. You have to simplify first, right? Simplify it first, and then we don't have to worry about weird rules. If I multiply this out, I'll get t squared plus 3t. This is something that now I can handle with basic rules. I'll throw an antiderivative at this, t cubed over 3 plus 3t squared over 2. We don't need the plus c because we're doing a definite integral. And I get to evaluate this between 1 and 3. If I go to substitute my 3 in, that's a 27 thirds plus 27 halves. And then I have to subtract off what happens when I substitute in the bottom number, 1. So this is 1 thirds plus 3 halves. A comment? Is this correct the way I wrote it? No, it's not. My fundamental theorem of calculus 2 is saying that we have to take, the antiderivative evaluated at 3 and subtract off the antiderivative evaluated at 1. Ftc 2 says subtract off the antiderivative evaluated at 1. It doesn't say subtract off the first term of the antiderivative evaluated at 1. So if I want to make sure that I'm subtracting off the full thing, please watch your order of operations. We are going to have to make sure that we've got parentheses on this bit we're subtracting off. So if I make sure that each of those things distributes, I can combine like terms a little bit here. 27 thirds minus 1 third, that'll give me 26 thirds. 27 halves minus 3 halves, that'll get me 24 halves. I can clean this up a bit, this guy cancels to 12. If I want a common denominator, I can multiply my 12 by 3 over 3. I'll get 26 thirds plus 36 thirds. If I add that together, that's 62 over 3. Or, alternatively, if you like your mixed fractions a lot better, you could say 20 and 2 thirds, or if you like your decimals a lot better, you could say something like 20.6 repeating. Okay? I'll do one last example and see if we can test out those new kx rules that we learned for the trig and exponential functions. If I go to evaluate this definite integral, again, first step is to antiderive. I probably want to rewrite this a little bit before I antiderive. Let's put this in a better form for us to work with, shall we? So, if I wanted to rewrite that second bit, we all know that being in the denominator means you can think about negative exponents. Having a root involved means that they're fractional negative exponents. Since I've got basically a half power in the denominator, I can flip that up to the top. Think about this as x to the negative 1/2 that I want to antiderive. And then I can actually antiderive my function. Right? We said the antiderivative of cosine should be sine. I do have to copy over my inside function. But since we're undoing chain rule instead of multiplying by pi, we have to divide by pi. That takes care of my first piece. Over here for my second piece, this is a power rule expression. I add 1 to the exponent up top, I get a half. I have to divide by that same number. That's my antiderivative power rule. This is what is being evaluated between 1/4 and 1. Now, before I do that, I'm just going to clean up that bit on the right-hand side a little. If I'm dividing by a half, I'm really multiplying by a reciprocal. So I'm really adding 2 times this expression. And most of you guys usually like writing roots rather than half powers. So this is what we're plugging stuff into. Okay? The top value always goes in first, so the upper value always goes in first. This means I've got 1 over pi times sine of pi plus 2 times root 1. And then I have to subtract off what happens when I plug in the bottom. This will be 1 over pi times sine of pi over 4 plus 2 times root 1 over 4. Whoop. Let's see if I can fix that. Sorry about my my messy pen here. At any rate, if I'm subtracting the top minus the bottom, like the warning from the last question, please make sure you watch your order of operations. We have to subtract off the entirety of what happens when we plug in the bottom, and not just the first term of it. Okay, so please don't forget that you have to subtract everything off. From here, I can simplify. If we know our unit circle, sine pi should just give me 0, so that drops off. 2 root 1, root 1 is itself, so that whole bit in the parentheses simplifies to 2. The rest of what I am subtracting off is, again, requires needing unit circle values. Sine of pi over 4 is root 2 over 2. Root 1 over 4, the thing I square to get a fourth is a half. So this is 2 times a half here, or just 1. That means when this negative sign distributes through, I've really got a 2 minus 1 that's happening, right? So 1 will be my integer term. I really can't simplify this pi and square root expression, so I'm just going to leave that guy roughly as is. Okay, my final answer for this particular question is 1 minus root 2 over 2 pi. That concludes our final makeup lecture for the semester. If anybody has any questions for me while we're here over break, because there is the homework due Monday, please don't forget about that. If anybody has any questions, please feel free to shoot me an email. Let me know. Aside from that, please try to enjoy your Thanksgiving break, guys.